Greetings, brothers and sisters. I am your host, your brother, your professor, Mr. O'Neil Barnaby, founder and director of the Black Math Academy, here with another video showing you what intelligent black society is all about. Today, I'm going to be talking to you guys about parent functions. Parent functions are your standard form of all of your equations. So get ready to get gamed up. Parent functions, so what are they in the first place? Other than them being their standard form of equations, they are a way of doing three things basically: tracing, tracking, and positioning. So where they can be used in the real world, anything that has to be traced. So a person fleeing something, or tracking, so you're trying to follow someone or some object, or positioning, trying to find out where it is, where this object or person is. So cell phones use this technology in terms of GPS. So thank you, Dr. Gladys West, the black woman who helped really pioneer that concept. Even though it does use signals, it still uses a parent function concept and algorithm. Tracing, so trying to follow where something went. You know how some car accidents, you're trying to figure out how in the world did the car end up like this? You can use parent functions as a way to kind of figure that out as well. And also tracking. If you know where one thing was and then where it ended up, you can figure out how to track it and follow it without being totally lost. All right, so with all that being said, let me show you what parent functions are all about. So I have 8 boxes here, so I'm going to show you 8 different parent functions that you're likely to run into when you get to your algebra and algebra 2 classes. All right, so the first one that comes up, y'all should be familiar with this one. Y equals mx plus b. Right, so y equals mx plus b is your standard form of what's called a linear function. Right? So linear functions behave the way you know. It's in the name, line. So when you graph a function like that, how it ends up behaving is like a line. So straight through. Nothing too difficult there, right? Okay. So the next type of function or parent function that exists, I'm going to simplify it into the equation y equals x squared. So y equals x squared is what's called a quadratic equation. And quadratic equations behave like what's called parabolas. All right, so when you graph a quadratic equation, a parabola is it's basically a U-shaped graph. So it behaves like a U. Goes up, goes down, and then goes up just like that. All right, the third kind of a parent function, I'll simplify this one into y equals x cubed. All right, so y equals x cubed is what's called a cubic function. Cubic functions behave like a backwards S, or like a snake. It kind of winds a bit. So when you graph that type of function, a cubic function, it behaves like, starts to come up closer to the origin, curves a bit, and then goes back up in that fashion. So it kind of sidewinds a bit, like a rattlesnake or something. All right, so y equals x cubed is a cubic function. Another type of function that exists, we have y equals the square root of x. So obviously it's in the name. This is a square root function. Let me write that down for you. And the way square root functions behave when you graph them, at least the parent function, they start from the origin and curve up, but it curves up very slowly as you increase the value of x. So that is an example of a square root function. All right, next up, we have y equals the absolute value of x. So obviously, again, it's in the name. This is a absolute value function. And when you graph an absolute value function, it behaves like a V. Right, so comes to the origin and goes back up in a V type of fashion. So far, so good. All right, after absolute value, we have a more difficult function, y equals 1 over x. So it's a fraction. In the realm of mathematics, they'll probably call it rational or even a reciprocal. That's another way of saying it as well. So let me say that. I'll just put all of them down. Fraction. Let me erase that. Sorry. Got fraction. Reciprocal. And rational. That's another one. Right, so those are your three ways of expressing the same function or naming it. And when you graph an expression like this, it behaves like, actually, it's going to behave like two curves going towards the origin and then going away from it, but opposite quadrants. So, to draw it, it's close to the x-axis, gets closer to the origin, shoots away from it, and then it gets closer to the y-axis as it goes down. Now on the other side, it does the same thing. Close to the y-axis, then when it gets to the origin, curves away, and then gets closer to the x-axis, but never actually hits it. In both scenarios, they never actually touch the x or y-axis in this example. All right. Following, we have y equals a times b to the x power. Right? Y equals a times b to the x power is an example of an exponential function. So I'll write that down. Exponential. And they can behave in two different ways. They can either grow or they can either decay. So it's in the name. Growing means it goes up, and decay means that it goes down. So I'll write that down too. Growth or decay. Now, when you graph that, I'll give you an example of the growth. Right? So it starts out really low to the x-axis and then shoots up all of a sudden. They'll just zoom up quickly, like very quickly. So that's an example of exponential growth graphically. Decay would be the other way. It would go down very quickly and then get very close to the x-axis. All right. Last but not least, we have x squared plus y squared equals r squared. X squared plus y squared equals r squared. That equation is an example of a circle. Right? I know it looks kind of weird, it looks strange. Most people probably didn't even realize there was an equation for a circle, but here it is. Right? So when you graph this, obviously, the graph itself will be the image of a circle. And the center of that circle is the origin in this case, as the parent function defines it. Right, so these are your examples of your parent functions, and mastery of these parent functions will then help you to understand what happens when you shift them. So when the function moves left or right or up and down, or even when it compresses or stretches, that can happen with these functions as well. So I'm going to talk about the rules and characteristics that make those things happen. All right. First thing you need to understand is that y is also equal to f of x. Right, so that top part there. Y is the answer to the equation itself. So you do all the mathematics and the answer you get is y. That's the result. F of x also represents that. The function itself is the mathematics that you're performing, And then once you're done performing all that math, it ends up becoming a value, a fraction, decimal, whole number, whatever it happens to be. That also is the representation of y or its answer. That's the first thing. So some of the rules that apply here is that when you take the function f of x and you add or subtract something to it or from it, how that affects the graph is that it's a vertical shift. So when you add something to it, it'll shift the function upwards by that value, whatever that number happens to be. So I'm going to call that n for now. So the function plus n or the function minus n. So plus n means it's going to shift up, and minus n means it's going to shift downward. So for an example, like this absolute value function here, since the corner of it is the origin, if I took this function and added 2 to it, using the origin as a reference point, it's going to shift that spot up 2 units. So it'll be on the value 2 on the y-axis, but it'll still behave the way it normally should, like a v, in that exact fashion. So f of x, or the function plus or minus a number, is a shift up or down. All right? If you take the function, but you add or subtract inside what's called the argument, or the input, the x part here inside the parentheses, so plus or minus and inside the domain, or the x, or the argument, that's actually a horizontal shift. So it'll shift left and right. But in this case, you're not going to follow the sign like we did in the beginning. Plus meant go upwards, which makes sense, and minus meant go down, which also makes sense. But when it's inside the argument, it's actually opposite the sign. So when we add n to the argument, it's actually going to shift to the left that number of units. And when you subtract n inside the argument, it's going to shift to the right that number of units. So it's either going to shift to the left or to the right, that number. Right? So an example would be like for this quadratic equation, if I put x squared, well, inside the x itself, I put x plus some number squared, it would shift to the left, whatever number of units that is. So using the vertex as a reference point, in this case it's the origin right now, if I put x plus 2 inside it and then squared it, it would shift to the left 2 units. So the vertex is on the origin, but when you shift it to the left 2 units, it goes to -2 on the x-axis. And that's where it would go. All right, so that's inside the argument. Next up, we have when you take the function and multiply it by a number, f of x times something, that ends up taking the graph itself and compressing it. So it makes it tighter, or thinner, which ends up making the value go up faster. All right, so if I take the function, like, let's say the linear function, so m is multiplying by the x, and if I took that value and made it a bigger number, 5, 10, 100, it would make the linear function compress. So it's going to get tighter, which means it's going to shoot up a lot faster. So multiplying by a number compresses it. It compresses the function itself. And then conversely, if you take the function and divide by a number, that'll be a stretch. So it widens the function itself. A good example of that would be, again, the quadratic one. If I took the x squared function and divided it by a number, divided by 5, 10, 100, what have you, it would take the U-shaped graph and make it a wider looking U. So it makes it more like a bowl, or like a lake or an ocean or something like that. So it'll increase, but increase just a lot more slowly. So that's what dividing by a number would do, rather. It becomes a stretch. All right, and then one last characteristic is when you take the function. supposed to be an f, and you multiply it specifically by a negative number. So -1, let's just say. So the y value, since f of x equals y, these are all y values. Take the y value and multiply it by a -1 or some negative number. That's what's called an inverse or a reciprocal. In mathematics, they'll give you the phrase a reflection. So it'll reflect specifically over the x-axis. So an example would be like square root. If I took the square root value itself and multiplied that by a negative number, that would make this value, the y value, is negative. So it'll flip across the x-axis into the y axis down here. So it's going up slowly in that direction. But if I flip it across the x-axis, it'll go down in that direction. Behaving the same way, just downwards now, in an inverse type of way. So multiplying f of x by a negative number is an inverse or a reflection. Specifically across the x-axis. Let me write that down too. Ta-da! And there you have it, folks. The Black Math Academy does it once again. We explain why we are clear, concise, and articulate, which makes us without peer. The Black Math Academy also shows you not just what you need to know, but why you need to know it and how it's applied into the real world. All right, don't forget to like, share, comment, subscribe, and follow all of our social media pages, our Facebook page, our Instagram page, and our YouTube page. And always remember that you should only debate your equals. All others, you teach. Math is where it's at.